So let's start with the next session on higher order optimization. And as promised, we'll talk about acceleration now. Uh, sim- so we saw AGD, and I'll just write down the algorithms just so that it's easy to compare how these higher order acceleration things have evolved. So AGD, one way to write AGD, as Alina mentioned, there are many interpretations, and I'll write one formulation for accelerated gradient descent. And let's see. So you start with at iteration t. So this was the gradient descent step. So for accelerated gradient descent, you do one of this, and let's do another step. I'll define another variable, and this one goes over the sum. Okay, so this is more like the iterate we saw in the morning. But so this together along with, so I've defined y, z, now it's time to define x. And let's say x1 gives you and we have these constants. Okay, so this is one approach to accelerated gradient descent, which this is like the lower bound that we saw in the morning. And another interpretation is this if you just minimize this, this tries to give you a point that's close to the optimizer. In like the point is close to the optimizer, the distance is close, and this one is the upper bound, and an interpretation is that this gives you the function value close to the optimizer. So in a way, you're trying to do both. You're trying to do something that's a trade-off of minimizing the function error and minimizing the distance to the optimizer. So for first order, we saw this, and this gave us a rate that went down as 1 over. We have used t here, so 1 over t squared with iteration t. And so for first order, we had this. The next attempt on increasing, going to higher orders, was by Nesterov and Bayes in 2009 and 2019 respective. Oh no, first we actually had something for second order, which was called accelerated cubic Newton in 2008. And then it slowly moved to higher order. The first attempts were by Bayes and then by Nesterov, and they give a similar algorithm. And let's look at the pth order version for this. So remember this, we have upper bound, we have this thing that gives, so we have something that gives you faster function error decrease, distance increase, and interpolation. So what Nesterov did and Bayes did was a natural extension of this. You replace this. So let's say this step becomes, so this is the Taylor approximation plus the regularizer that we saw in the previous lecture. So the same thing. What do we have here? So this part remains the same. The next part, actually, they modify it a little bit to use the same function.
Is there to norm?
Huh? Yeah, it's still 2 norm. Everything is Euclidean. Yes. So now you have the same linear combination of these xi's. But the regularization here is minus x naught to the p plus 1. So they changed this to p plus 1. They changed this to minimize the upper bound in this case. And, oh yeah, sorry, okay. And then the next one is, and then the same xt plus 1 was again and these constants are again the same, but now you use the 1 by the pth Lipschitz constant.
Your notation, the return value is what?
Oh, so the good. So the return value is
YT.
yt plus 1.
YT or not? There's no averaging like Helena did.
No, there's no averaging. We're just returning the last yt. Right? And it's the same over here. Yeah?
Oh, so I have another question. So like here, okay, so you know, like you have like the y, which is like a gradient step,
Yeah.
and z, which is like a mirror descent step.
Yeah.
And like, so basically, previously you gave us the gradient descent version, like for minimizing that, for doing this order optimization.
Yeah.
Is there like a mirror descent for that?
I don't think we know a mirror descent version for that yet.
Okay.
Yeah.
Can I ask why you say that z of t is like a mirror descent?
Well, I mean, you know, like usually.
Like if you look at this step, for example, for the L2, for p equals 1, this is kind of what you do, the mirror descent when you're in Euclidean norm. It's like you're taking an average of these subspaces and some regularizations.
Because of the sum.
Yeah.
Because because of the sum. Like okay. I see the point.
Yeah.
I guess also you said in the analysis, like the function error of yt is considered and the distance of zt to opt is considered. Right?
Yeah.
So it's maybe not an algorithmic answer, but like a structure of the
Sure.
proof.
Yeah. Thanks. Yeah, that's good. Okay, right. So after doing this, unfortunately, we don't get the optimal rates, and the rates that you get, it converges as something like e to the 1, e to the e plus 1. Okay, but now if you want to see the optimal algorithm, and I'm going to change this one here so that we can compare it to that. So the optimal algorithm actually for p equals 2 was given by Montero and Schweiter in 2010, and that algorithm gave a rate of convergence that was 1 by t to the 7 by 2. So the accelerated cubic Newton gave us something that's 1 by t cubed, and what these people gave was 1 by t to the 7 by 2, which is slightly better, and this is optimal actually. Okay, so let's see what the optimal opt higher order. So this was first given by Aaron and co-authors in this paper that's near optimal acceleration, which is an extension of the Montero-Schweiter framework to pth orders. Yeah, is that right? I forgot the co-authors.
Do you want to say the co-authors?
Yeah, let me see if I remember the co-authors.
Sorry, I'm just, there were 3 groups around the same time that all had this.
They all
result,
had the
and
same.
It was all posted in a joint paper in Cult. So there's a joint paper with a number of authors.
It's
and it's only optimal up to a log
factor.
Okay, no.
Yeah. Okay. So let's see what this algorithm looks like. So the first change is, let me write this. So the first change is this is not a constant anymore. This depends on something. So it's changing. The next thing, so this part, let me change this. scalar. Okay, so this part still remains the same as the non-optimal one, and this one, this remains like this. So this is the same as the first order one. So now the regularization is basically still a squared instead of p plus 1, and the trick that comes now is, so the first thing I'm going to do is move this up here. So xp is okay. The first thing is we do this, and I'm also going to be a little hand wavy and say that lambda t, so that's the thing I've not defined yet, is something like yt. Okay, let's look at the t plus 1. Okay, yeah. Good. I'm going to say yt plus 1. Okay, so I'm going to, so if we look at the algorithm, we're basically still working with these ratios, which is changing with iterates. And I want to say that this lambda is something like this. So if you first look at the algorithm, you see that yt plus 1 depends on xt. Or before that, xt depends on at, and at and at plus 1, and these depend on lambda I. Lambda I depends on yt depends on, xt. So it's kind of like a circular algorithm, and you may ask, how do we? But suppose you knew what lambda t was. So if you knew what lambda t was, this algorithm is well defined and it's straightforward. But if you didn't know what lambda t was, then it's like a circular circular definition. So the way to get around this is you do a binary search, and we know how to do a binary search and guess a value for lambda t. Once you have this, then you run this algorithm. So for now, we'll just assume we know lambda t. So that makes a lot of these things easier. Okay, so this algorithm is actually known to give a very good convergence rate. So it should go down as 1 by t to the p plus 1 over 2. And this is known to be optimal. So this is all up to logs, and you can get this convergence rate. Okay. So I'm hoping that let's see at least how do we prove this algorithm. And this is going to hopefully present a very simplified version of this proof. The original proof is not so simple, but Arun here has managed to give a very simplified proof for this, and I'll be presenting that. So let's look at that.
Specialize it to t equals to 1, you get t squared. Right?
Yes,
Is the
which is the same as
yeah.
accelerated.
And but is the algorithm which seems to adapt the rate or various parameters based on the sequence of steps. Does it make the analysis of the standard equal to case more transparent or easier?
Okay, that's a good question. So the question is that does this for p equals 1 make it much more transparent, the analysis?
It's sort of like
Yeah. I think for p equals, so this is an extension of Montero-Sweiter algorithm, by this algorithm by Montero-Sweiter acceleration, which is slightly different from AGD in the standard setting. And that also has these implicit step sizes. So I don't think it really gives a lot of insight into AGD in the for p equals 1.
So if p equals 1, then lambda is just 1, right?
Oh yeah. If p equals 1, but there's still.
Nothing. Everything's explicit.
Oh yeah. When p equals. But Montero's fighter is not quite explicit.
Well, I think they're doing like approximate points. You have to solve this problem exactly. That's where the implicitness comes from. In the version you described, there should not be any implicitness.
Okay, yeah.
Other than like,
So P is 1, that's 0.
Yeah, p equals 1. This is.
Simple thing.
basically the point is, when p is more than 1, right? Basically the point is when p is more than 1, there's some slight non-implicit lift, there's some circularity in the step. But in the Montero's Fader paper and most follow-ups, you can sort of realize that by binary searching over this, you can input a value lambda or guess a value lambda and then get out this lambda t. And you can make them match arbitrarily closely, and it's only cost like a log factor.
Out of curiosity, there is no hope that it is like a fixed point problem that you can solve because it is a contraction. I'm just asking. It's the first time that I see it, and I'm just asking.
Fixed point problem.
Like it is circular, which is equivalent to my language that it is a fixed point problem.
Okay.
I don't know if there's like a fixed point interpretation of it.
Okay.
There might be.
Yeah.
I don't know.
Yeah, it's not known yet. I guess.
As a type of answer to your question, I think there are like general frameworks towards what's being discussed that I think are rather nice and clean. But yeah, in the case when you're doing acceleration, this thing of some sort of circular dependence on this lambda just doesn't arise. So there's maybe a clarity in seeing the general framework, but there's also genuinely a complication that seems to arise when you go beyond p equals 1. At least that's my intuition. That's all. I can tell stories about that broader story later.
Okay. So for proving this, the first thing we need, which let me just call it lemma main, is so let's define this potential function, which is just this AT times a function error. So the potential function is just tracking how much you have gone down in the function value and how close are you to the optimum. And what we can prove is, we like this. So then basically phi t plus 1 Okay. So the first thing we need is, if you just look at this potential function, this is decreasing at something that depends on lambda and depends on this. And if you assume this, first let's see if you assume this, then how do you get the rate that we are looking for? And see that. So we will still think of, lambda t to be just we'll just assume this. And so if you look at this AT is basically an increasing function. All these a's are positive and it's all true. So you can look at this partition. So let's start at A0, A1. So this is, let's say, the number line. You have some AT to the final iterate. And if you just look at this, in the end, you want So in the end, you basically want AT to be something that's like phi 0 by epsilon or so. This is just because if we do some, suppose you can do some induction here and phi t plus 1 is at most, let's say phi, I mean, you can do an induction, ignore this, phi t in the end is at most phi 0, and you want this function, you get this AT from here. So you just want to look at AT until this point, and let me just look at some point and divide this into phases. So these iterations, let's say, these iterations are such that these a's are less than some 2 to the I. So let's just look at one of these phases and see how many iterations can you actually have in each phase. And so for this phase, so we're just looking at the iterates. Oh, sorry, hard notation. Let me call this new. So we're just looking at iterates so that this capital A is just between these. And for such iterates, we can, let me classify this into 2 times. So let's say T1 is the, okay, wait. One more thing is I'm going to call this as R. So I'll just call this difference as B plus 1. So I'm going to classify this into 2 parts. So one is the total number of iterates such that this RT plus 1 is less than some threshold R, which I'll choose later. And T2 is greater than R. And we'll just see how many of each can you have. So let's start by bounding T2. So if you want to bound T2, let's look at this potential again. And what we know is that phi t plus 1 is lambda t is just r to the p minus 1. So just from this potential decrease argument, you just get this. And now let's say r t plus 1 is at least r. So you can get this. And we don't want this to be, we basically have that this is at least 0. And if you want to bound the number of such possible steps, you would basically get that T2 is at most, let's see, 0 by sum of AI. Oh, before that, let's also see. We also know that these A's are in this range. So I'm going to replace this by 2 to the nu. And then you can just say that this is at most. So this is the maximum number of steps you can have of this kind. And then to look at this, I'm going to use this fact that's proven in most of these acceleration things that basically says so once you're given this fact and you're given this bound, this basically means you have so this is just using that RT plus 1 is greater than R. Oh, sorry, is at most R. And this would just give us something that's t1 by. You can have at most these many of such things. And we also know that, so you can basically say that, so this is at most, and this, so let's, is at most 2 to the, again, because we're in this one phase. So from this and this, we have the total number of iterations in each phase. I want to balance out these values. So you have that the total iterates in, let's say, phase new is bounded by some phi 0 by this, let's see, 2 times this times okay. So you want to balancing these out, you can actually set R to be something that's something that's of this sort. So if you balancing these, you can set R to be this, and once we put it back into the total time, you basically get that this is some 2 to the new times 2 by plus 1. So this is for phase new. You can, by splitting these two kinds of iterates, you can basically show that you get something that the total iterates are some 2 to the new raised to some 2 by 3p plus 1. And now we, so the total, so you want to sum it over all phases, and the total time is number of phases, and this is also an increasing function because 2 to the new keeps increasing. We're increasing new, so this times max value of, and so this is something like log n, log 1 by epsilon, let's say. And the maximum value of nu that you want is phi 0 by epsilon, and that gives you something that's 0 by epsilon to the 2 by 3p plus 1. So this gives us the rate on epsilon, and if we look back, it matches this. So if you want this to be less than epsilon, the number of steps you need is proportional to 1 by epsilon to the 2 by 3p plus 1. Right. So what we showed so far is if you assume this, then you get the right convergence rate. Now, are there any questions? So right. So now this is the main place where we actually need all of the modifications that we saw from the originally proposed AGD. And I'm going to cheat a little bit more in trying to prove this. And so I'm going to cheat a little more, and I'm going to say that instead of yt plus 1 minimizing this, going to cheat and make yt plus 1 minimize this instead. And you can actually believe that you can implement this using a few number of the original minimization problem that you have, but going to cheat and I'm going to say that let's just have y t plus 1 minimize this. So let's look at two things. What does this yt plus 1 mean? I mean, let's characterize this and this next. So I'll just use the optimality conditions for both. And what you get is, so let's go here. So we can say that gradient f of y t plus 1. Oh, sorry, I also forgot that I want to lambda t and square. Yeah, sorry. So I'm going to cheat and solve this. So since our lambda t was basically yt plus 1 minus xt, it's almost the same problem. So from optimality, this is just by differentiating this and setting it to 0, we get this. And we saw it this morning that if you just minimize these, then you actually get oh, sorry, I forgot one more thing. This has to sorry. This algorithm, it's not on X. We're going to change it to be using these Ys. And this should just be okay. So we have these characters. So this is what we know about the iterates, yt plus 1 and zt plus 1. And now let's prove our original thing. So I'm going to split it into two parts. The first one says that I'm going to look at this term. I'm going to lower bound this by I'm going to say this and also going to give an upper bound on this, or rather I can give an equality that this is okay. So given these two, you can see that this directly follows. Your phi t is just this plus this term, and this is at t and at t plus 1, and you exactly get that back. And to prove this, this one's much easier. So this one actually just uses convexity. And this one uses these in some way it just uses the cosine law. And an easy way to see this is I can replace this. So from optimality, you have this. And this is just zt minus zt plus 1. So this is just equal to once you have this inner product, you can use the cosine law, which is basically that if you have, this is then exactly equal to this with, so this is exactly equal to and this is easy to verify if you just expand these. And once you have this, then we again, so then we do two things. We replace zt minus zt plus 1 first using this lemma. So this just becomes at plus 1 squared. And then you can use this first point to replace this gradient with get lambda t squared. And from the way we choose these coefficients, which was here, sorry, so many typos. Yeah, but so from that, this just becomes at plus 1. This constant changes to this. So this part was easy to see. And for this, we just want to use that the function f is convex. And you can do some splitting and actually just this directly follows. That's an easy exercise to see. Yeah.
Sorry, so I just so for the second one, can we get it directly from the optimal condition without actually having to do that rechaining that you did at the beginning?
Oh, you mean can we get this?
No, I mean IR.
Oh, this one? That's good. We're using, so this is where we're cheating, basically,
Okay, I see.
to get this. Correct. So if you combine this, use some convexity, you get that. And this is just cosine law. You can combine these, and this gives you potential decrease. And yeah, so this is a much easier proof thanks to Arun. And the original one had a bunch of more intricate things. And we're still ignoring the fact how to do the line search and that we're changing this to an easier problem. So yeah, so this is what I wanted to present today. I'm happy to take questions.
Thank you. Questions?
Yep.
So you mentioned you mentioned some applications to discrete optimization for these higher order methods.
Good. Or discrete as in these CKMST kind of.
CKMST.
Yeah. Yeah. Okay. Right. So this is a higher order extension of these Montero-Schweiter acceleration framework. There's a work. The easiest way to see this is you can use this kind of acceleration in this Oracle, in this new kind of Oracle model, which was defined, which is in this paper called acceleration via ball Oracle. Acceleration via ball Oracle. And this ball Oracle, and that's again by Aaron, Arun, Kevin, Yujiya, and who else? Okay. And
Yuntat's on it, Teacher's on it, and Yair's on it.
Yair and Yintat, yeah. So in that, they basically use this Oracle where you are allowed, so you're given let's say in a small Euclidean ball, you can exactly minimize the function. And given this, standard a naive gradient descent kind of approach, or rather a naive approach where you just move to the new minimizer of the of the function inside, like you keep shifting the ball like that kind of gives you a rate that's the initial total distance divided by the radius of the ball. So to converge and times some log 1 by epsilon. So you can use this kind of acceleration to speed it up to, let's say, so you had something like the initial distance, say d by the radius of the ball, r, you can speed it up to d by r to the 2/3 using this kind of acceleration. And once you do that, there are direct applications for softmax and these regression problems. And the way to see that is, so you can implement these ball oracles very easily for these softmax and some regression kind of problems, because softmax has this property of Hessian stability. And with that, I mean that the second order derivative does not change a lot outside a small range. So in this ball, basically for softmax, the Hessian is kind of it's off by, let's say, a constant factor. And because of that, you can implement these ball oracles very efficiently. And once you have this softmax, so you can think, so once you have softmax, that means you directly have something for infinity regression, and that means you directly have something for max flow. And the rate that you actually get is, so I said you have this d by r to the 2/3, and so you can think of d initial distance as something like m to the 1/2 if the size is m. So once you can go from m to the 1/2 to m to the 1/3 in this particular way. I guess that's very sketchy, but I can talk more offline. Or you can ask Arun more. Yeah.
Any more questions?
Both of them would be high level, but and also it could be like related also to the first order. The first one is like in the equation of ZT, alpha t is like preconditioning, like it's changing together. It is multiplied with the gradient. Is there a version that it is post conditioning? I don't request necessarily, but out of curiosity, like is it even that detail super important to have acceleration, like having alpha t outside of the sum? This is one question.
Oh,
This is one question that I have, and the other question is like very nice. Like accelerated descent is a thing that always takes time to understand the proof. I have a question like in non-Euclidean spaces like manifolds, there are like very esoteric, I would call them, at least papers that they say, look, there are some lower bounds that you cannot do acceleration. I try to follow a lot the proof. Can you spot out like, here is the moment that we used a lot the Euclideanity of the space?
Okay, so for the first question, these AIs being different is actually like in the morning session, Alina explained, you're kind of looking at hyperplanes, and you're looking at different hyperplanes that are below the function. Because it's convex, you have these hyperplanes. So when you look at these different hyperplanes, eventually you don't want to give the same weight to every hyperplane, because some of them are more important and some are not. So these being different is kind of helping you get a better hyperplane that is below the function. And the second one, I mean, we're taking these optimality conditions and these derivatives, so that's very Euclidean.
So it's like the last lemma that you present.
Yeah, like this one is,
I see.
but I think you can extend these to non-Euclidean norms. Am I right? Maybe Arun has a better answer to that, but maybe you can extend these to non-Euclidean norms, but beyond that, I'm not sure. Yeah.
Any other questions? Right, let's think again. So that's it for the program today. I was asked to make an announcement from one of the social organizers. I believe there's music night or a music event going on. It should be advertised on the Zulip, so you can check it out there. So that's happening this evening. And we'll be back tomorrow morning with the program with coffee at 9 and talk at 9:30 for our last day of this boot camp. And friendly reminder that tomorrow at 11 a.m. is when we'll have the town hall towards us deciding how we want to organize things for the rest of the program. So think about that. Feel free to come find me in chat, and I look forward to seeing you all later. Thanks. Thank you, guys.